really 2 more lectures that are pretty easy to consider. So if you're at all feeling like it can't go on anymore, you're so tired, this is too much, push through it. Well, you still have, so you have a lot of points to consider for lab and a lot for lecture. I'm gonna talk more about the lecture, the grades and stuff like that tomorrow. So anyway, let's get back to this. So I mentioned that the commissures that are these white matter within the brain that are largely responsible for sending signals long distances, and this corpus callosum is the one that sends signals from one ventricle to the other, or one hemisphere to the other. One of the things that this says is that the left-hand hemisphere is largely a function of mathematics and speech, and the right is three-dimensional spatial representation, and then recognition, musical ability, recognition of faces. One of the things, so that's not complete, right? And the other thing about this is that you can have well-developed areas of one part of the brain and not a very well-developed area in another. So for instance, a number of years ago, our mother had passed away, and so I was, my brother and I were packing a vehicle and to take stuff out of her house, and my brother goes, "Oh shit, this isn't gonna fit." And I go, "Frank, what are you doing?" And he goes, "What?" And I took it out, rearranged it, and he goes, "How'd you do that?" And it all fit. And I said, "Spatial recognition, right? It went together, right? And he was like, he had no idea what the hell I was talking about, right? So anyway, I showed. So I'm pretty good at that. A number of years ago, in one of the PBGR papers, there's a former student who wrote a paper called something called prosopagnosia. Prosopagnosia, I had never heard what the hell that word was. I had no idea of what it was, but it's something with recognition of faces. It's an inability to recognize faces. So you wake up in the morning, you meet someone on Monday, you wake up on Tuesday, you have no idea who the hell they are. Your family members, you say, "Oh, hi, you're my wife." "Oh, okay, nice to meet you." And the next day, you have no idea, you forget who they are. So I found, I think it was maybe Mrs. Gaspar, one of us found a online survey, a test of this condition here. How close are you to this condition? And Mrs. Gaspar got 100%. She was able to recognize parts of faces, and she was like, "Oh, this part right here, it goes to this one." She was perfect. I, on the other hand, was like 1 point above having this condition called prosopagnosia. I had no idea what the hell I was looking at. I was like, it looked like there was just some part of it. So these pictures, let's just say I got a picture of Janelli, and the whole picture's right here, and then I take one little sliver of her face. Mrs. Gaspar was like, "Oh, that's definitely Janelli." I'm like, I got no idea who it was. And so the computer told me that I was very, very close to having that condition. So my point here is that these areas right here can be well developed or not well developed, and I'm not sure if it's gender related or not. I don't know. Right here, but there's a lot of redundancy too. So I'm not going to say to you that the right hand hemisphere doesn't do math and the left hand hemisphere doesn't do spatial recognition, right? Because that's not true. Right? So, but generally speaking, this is true. Generally. So now let's get back to way back at the start of the unit 4, when we're starting to talk about neurons. And we talked about neurons sending electrical signals. Those electrical signals are a function called action potentials, and those action potentials are a function of the sodium-potassium pump. That trigger of the sodium-potassium pump causes the movement of ions across the phospholipid bilayer through those gated ion channels, some of which are Ligon gated or maybe electrical gated, right? So those channels then are important recognizing. And what they then produce, if there's an individual one, you can see that characteristic action potential pass through that axil lemma. But if there's a whole mass of them, then you can see other different patterns here. And if you look on the right-hand side of this drawing right here, you can see brain waves that are made by, we've talked about MRIs or magnetic resonance imaging. This is called electroencephalogram or EEG. This is measuring the brain electrical activity, again, from a series of those sum of action potentials here. And those, if you take thousands or millions of action potentials and you sum them together, they're gonna produce these different patterns here. Alpha, beta, theta, and delta waves. And these patterns here mean something. So when your eyes are closed and you're nearing or are in REM sleep, then your brain's gonna produce this alpha waves. The beta is when you're hopefully intense, not what Victoria is doing right now, yawning, but hopefully you're intensely paying attention. I just wanted to pick on someone and I saw you doing that. So hopefully you're in beta, your brain's producing beta waves. Hopefully you're not producing theta waves, which is frustration in adults. And definitely I don't want you producing delta waves, which is deep sleep. So these waves mean something here, and they're associated with, if you look at this time right here, this is sort of how brain waves change over time as the person is sleeping. So they're awake and they're going to be producing one set of waves, and then as they go into deeper and deeper sleep, they progress to different types of waves right here, and then they go up into REM sleep, or rapid eye movement sleep, and those brain waves will produce something different, and then they sort of go into and out of REM conscious or REM sleep here throughout the time, and then they return to consciousness up here on the right at the end of the time. So that understanding how those what those brain waves look like, and especially this one right here, these different waves, and how you can diagnose this wave or that wave and associate with either children or frustrated adults, that's important. Hopefully, you guys are going to use this part of your brain, the memory, the working memory, the short-term memory, and you're going to transition it hopefully to long-term memory. So there are different parts of memory, there are different forms of memory if you're going to perform a task. So you're going to take that working memory. If I give you a phone number and I say, dial that phone number right now, you might immediately forget it right after you dial it. That is in working memory. If you retain it for a couple of minutes to days, that's short-term memory. And then I, a number of years ago, got a random contact from email from on LinkedIn. And this guy sends me an email. And at first I was like, who the hell is this? And then I said, oh, are you the Jeff Diamond? And then I proceeded to tell him, say what his original home address was 130 years ago. And then I also told him his phone number. And he goes, holy shit, I barely even remember that phone number, because remember, I changed it, they changed it on me in high school. And I said, yeah, that phone number then went to this phone number, it's 522-0075. His original phone number was 396-8973. Right, now why do I remember that? I used to call him all the time, and I would dial the same number all the time. I didn't have memory, right? I had old rotary dial phone numbers right here. And so why, and where in my memory is that here? Is it in short term? Is it in working memory? No, it's in long-term memory. When you do something repeatedly and you do that working memory task repeatedly, successfully, in different conditions, in different locations, under different circumstances, then you slowly transition it from working to short-term and ultimately to long-term memory. That's what you're hoping to do with this content, I hope. Because if you do, then it's going to serve you better in at least AMP2. This consolidating and strengthening synaptic connections here, that process right here is, and remember what I've done at the start of each of the units, except for this unit, Hey, what did I do? I tried to give you something to draw. I tried to give you something to write. I tried to give you something to do so that you could perform this task that was directly related to this topic, the topic at hand, so the muscular system, skeletal system, etc. And I tried to give you something to do so that you could help, it could help you push that from working memory to short-term memory and hopefully again to long-term memory. There's other types of memory here. I don't know, declarative and procedural memory, but those things are not nearly as interesting to me, particularly in context of studying and stuff. So again, working memory is a short-term duration memory, and you want to transition it to long-term memory. So I just showed you that I either A, remembered 2 phone numbers from a long time ago, or B, just totally lied to you about those phone numbers, and you have no idea which one it is. I definitely remember those numbers. So generally, what that means is that I do have some things in long-term memory. My brain is still functioning, and even though my brain is still functioning, there is a gradual decline in my brain in terms of the size and the sensory and motor function. There's a number of different things that happen throughout your life as you get older. One of the things is that my sleep pattern might change here. Long-term memory generally is unaffected. Short-term memory is more affected by gradual brain CNS or brain decline. When you get severe examples of that, there's chronic neurodegenerative diseases. One particular one is called Alzheimer's disease, and there's different forms of dementia, and I'm not going to ask you to distinguish between them. If you're interested in talking about football here, there's also early onset dementia that is function of too many blows to the head. But on the left-hand side, you have, if you look at this picture, on the left-hand side you have a healthy brain, and on the right-hand side you have an Alzheimer's ridden brain. And if you look at this brain, it looks, the whole brain looks a little bit different than the on the right and the left. There's a little bit different. But if you look at the cerebral cortex, if you look at the section here, in particular the hippocampus, so these ventricles here on the left side are relatively small, and that space is occupied by the neurons themselves. So this space right here is occupied by the neurons, and that is part of the hippocampus, and it's associated with memory. So in general here, shrinking of the cerebral cortex is associated with a loss of memory, and particularly a loss of short-term memory and working memory. So these shrinkages of these areas here, these are largely a function or a characteristic of Alzheimer's disease, and there's CTE, or chronic traumatic encephalopathy, or CTE, and that is, it's going to, the result is, causes is different here. One is through blows, repeated blows to the head. The other is through chronic degeneration of the brain. Generally speaking here, there's 2 things that are focusing here in context of Alzheimer's disease. There are these things called amyloid plaques, and what they do is these proteins that are produced by the body, and they attach to the axons and to the dendrites, particularly to the axons, and then they damage the axons. They prevent the axons from setting action potentials, and they also produce the brain's also producing these neurofibrillary tangles here. These tangles, again, are preventing the sending of action potentials. So as a result of that prevention, the brain is no longer functioning as accurately or as well, and that results in severe shrinkage of the cerebral cortex. That's a chronic condition here. Here is an acute condition, hopefully. Here is 2 examples are hemorrhagic and ischemic stroke. Either bleeding from the brain or arteries are blocked in the brain, both of which are going to produce the same thing, right? That same acute condition is called stroke. And if you look at this MRI image right here, there's areas that are lit up in a different color. So this area, this white area right here, and this area right here is going to be the area that's affected by the stroke. If you look at this area where I am, where my pointer is right now, that might be close to, depending on what slice we're talking about, that might be close to the temporal area, and that could be affecting speech recognition and speech production. So there's two conditions that can affect the brain. One is chronic, one is acute, stroke or Alzheimer's. So if you talk about the stroke here, the stroke can affect other body systems as well, and that's sort of illustrated here. But in particular, we're going to worry about the motor skills and the sensory skills that a stroke might affect, or the Alzheimer's might affect, in the context of memory, learning, and speech production. All right, so with that, we're going to stop right here. Tomorrow we're going to pick up here talking about the cranial nerves, and I've already given you a little primer on the Roman numerals, and we'll talk a little bit more about that, and then we'll do another transition to another thing. So are there any questions for me? Okay. Thank you very much. Once again, we are almost done with this material. We're almost done with this class. Power through it. Don't forget to do your LT assignments.